Okay, hello everyone. My name is Elias, and I'm here with you with CyberPlus Quantum Program. This is an interview series. Each episode will invite different experts from academia and industry to talk about the latest trends in this field and how we can bridge the gap between academia and industry. So here for the first episode, we start with quantum expert. The reason is that, as you may know, 2025 has been named International Quantum Science and Technology. So it's kind of like shows the importance in this field, and so let's just start with this field. So as the first guest, I'll have Mandana Bidarvand here, and she did a PhD in applied mathematics from University of Saskatchewan. And she worked in mathematical modeling, stochastic process, theoretical physics, and massive quantum coherent structures and infinite qubit arrays. So, and now I present you Mandana Bidarvand. Yeah. Hello, Mandana.
Hi, thanks for your introduction. Yeah, I'm very happy to be here.
Yeah, thank you so much for joining us. Today is a pleasure to have you here. So I start for the first question. Let's start with the personal side. And I want to know, like, what first inspired you to pursue a career in quantum field?
Well, my path to the quantum world wasn't really a straight one. So I studied applied mathematics in my bachelor, and I studied financial mathematics in my master's. And now I was always interested in complex systems and how to deal with them and how one can apply all these math rules that we learn to a real world problem. And then when I was doing my financial math for my master's, I learned a lot about randomness, stochastic processes, and how they work as an important characteristic in real systems known as noise, basically. And I think I started looking at quantum computing and quantum knowledge basically very first time when I realized that I can apply this randomness and all these rules that I've been going through in quantum systems, in real world problems, and actually make a difference in this science, the material science, all that has been working on right now. And I think that was the starting point. I needed something more than just dealing with financial assets and stock price markets. So yeah, that's how I started working on quantum computing.
So that's very nice, actually, because you work in the finance and stock market, right? So we've got a lot of questions this day in this field, especially what happened. Anyway, that's irrelevant to our conversation. Let's get to know that. Can you share your journey into this field, like any pivotal moment that you had or whatever that actually shaped your path?
So it was a very continuous movement towards this path that I'm taking right now. So as I said, I started with applied math. We dealt with a lot of programming. We learned different languages, and we've learned about optimization problems, how one can apply it to make any sort of problem better. And then after that, I learned the stochastic processes and randomness. I learned that those are known as noise in real-world systems. So then my supervisor, Dr. Arthur Soa, he was mainly working on massive quantum structures, and I came across a few of his works, and he actually had some, in the past, he used to work with some of his students on some financial and the stochastic problems. That's why it caught my attention. So I started reading his works and got in touch with him, and then I got admitted to do a PhD with him. And at first it was very new for me because in the first year of my PhD I had to take a lot of physics course, and it was very new. Well, I mean, I took a few physics courses back then, but not a lot, not quantum physics. So yeah, I can say that I am still learning about all the basics, about all the fundamental concepts every day, and I'm really happy I ended up taking this path. And then right now, after finishing my PhD, I talked to Dr. Robert Green, working in the physics department. He does a lot of work. Well, he's a physicist, and he has a lot of projects working on quantum materials, and he closely works with the synchrotron in Saskatchewan. So he does a lot of real-world, interesting projects, work on real good projects, and that was very interesting for me. That is always my main goal, to find real-world application for what I've been doing. So yeah. And now I'm here. I just started my postdoc, and it's been a month, and I'm very excited.
Yeah, for sure. That looks very exciting, of course. Yeah, I will say, like, after watching this movie from John Nash, Beautiful Mind. So that's really true. The mathematicians are the beautiful mind in everywhere. You see that really in the conversation that you have, and that's of course very inspiring. So, who are some of the scientists and mentors actually who influence you, inspire you along this way?
Well, if I want to name scientists, well, there are a lot of, there's a long list of mathematicians and physicists that I was always inspired by their work and their resilience and learning more and more. From the top of my head is Feynman. With his famous Feynman diagrams, and John von Neumann, a mathematician who did a lot in this interdisciplinary area, physics and mathematics. And I think these are the two of the biggest ones that I've always been inspired by. And among my mentors, I was always really fortunate enough to have really great mentors to teach me how to think about a problem as a mathematician, especially when I transitioned to the quantum computing and quantum physics, and I have to obviously learn a lot and lots of new things for me to learn. And my supervisor, Arthur, really helped in shaping my perspective, a new perspective to look at problems. And Dr. Steve Ryan, I've always enjoyed his lectures and the way he approaches a problem, the way he explains a problem. And he is always doing a very super interesting project, which is interdisciplinary between music and math, music and topology, quantum math. And it's just very nice to have mentors like that around you. So yeah,
that's very interesting. Like in USask, we have a lot of this phenomenal, inspiring scientists, like as you mentioned, like Dr. Soa or Dr. Ryan, and some others that actually do a lot of these innovations. Kind of like interesting. Like I've been always thinking how mathematicians also have a very good sense in music, but I'll get to that part later. Let's kind of like ask a question.
Yeah, it's not just music. I've just became to realize that not only music but also philosophy. So art and philosophy are a common topic between mathematicians, I think.
Indeed, it is. Yeah, of course, you're right. That's true. So let's move on to research and achievements. So, can you briefly explain what are the current research in quantum computing and what excites you most about it?
Mm-hmm. So currently, so I have to explain a little about what I did in my PhD. So what we did was to introduce a new language to discretely represent qubits, which are the fundamental elements of quantum computing, and continuous functions, so to speak, in this specific Hilbert space and so on. And this language is just a new framework that can be used on so many different systems. And right now, in my postdoc, we are hoping with Dr. Robert Green, we're hoping to apply this same methodology on different Hamiltonians in hope of finding new structures and being able to introduce or to somewhat scale these huge Hamiltonians, because as the scale goes up, as the number of qubits increases, the system gets larger and larger, and it's really hard to keep track of the coherence between these elements. So that's one of the challenges, and we're hoping by this methodology we are able to break down or sort of introduce this new representation to each Hamiltonian to simplify things for us and be able to actually look at the spectral properties, which is something very important when you're working on quantum physics models.
Right.
Basically, yeah.
Yeah, sure, indeed. So what are some of the biggest breakthroughs and achievements you've been part of during your career? Especially, I'm talking about the PhD that you did in USask.
Mm-hmm. Well, I can say that getting my PhD for me personally was a breakthrough. And I think it was a very great achievement for me. There were so many moments that I thought, I don't think I can finish this. I don't think I can do this. Or for whatever reason, it's hard to live so far from home with your family away. And so many other things. But I think the more you try to be encouraged and focus on what you're finding, and if you really love learning new stuff, that could fuel you for difficult paths like this. So, and throughout my PhD, this was a moral story, but other than that, I was always rewarded so during my whole PhD, I was rewarded the graduate teaching assistantship. And then I was also rewarded the graduate research fellowship during my PhD. And yeah.
Nice. That's great. Yeah, thank you. Actually, that's talking about it. Like about the life as a PhD student. I understand it can be difficult at times. So yeah, thanks for sharing that. So quantum is often actually considered really abstract. So, and a complex field. So how do you make your work accessible to a broader audience? I've been a part of your seminars, actually, some that we did together and some that I've seen that you presented your work in, for example, in Quantum Days in Calgary that we did last year, right? That we attended last year. So you want to explain how do you kind of explain it based on the audience that you have and break down this math so people can actually digest it?
Yeah, so I think the biggest challenge is to try to simplify a huge model that you have with so many different technicalities in there. But I always try to break it down into its simplest parts. Then I pick a starting point for myself and I always check in with the audience and make sure that they're following how I'm going and it's working. And using examples, real world examples has been very helpful. Using images, pictures, any sort of representation that I can offer really plays an important role. And for example, when I explain a concept like superposition, which is one of the fundamental properties of quantum system or quantum elements, I would use this metaphor, or it's not a metaphor, it's I would say, if you play a single note on a piano, you just hear one note, but then when you play a few of them at the same time, you have a chord, and there is harmony, and there is a reason, there's a science behind why those notes sound very nice. Some of them sound sad, some of them sound happy, and that harmony, when you're playing everything together, this is exactly like superposition, because the superposition is the characteristic that enables the qubits to be in multiple states, different states, all at the same time. And that creates a harmony, which is like a, for system that can actually signifies or resembles how this superposition actually works. Because superposition is like, when you think about it just very briefly, it can be really magical, right? Because you'll be like, okay, what do you mean if I don't open this box? And then you don't know what's in it, so it could be anything happening in the box. And I'm referring to the Schrodinger's cat experiment, yeah.
Right.
But yeah.
But that's nice, actually. Probably actually talking about music, people can understand it much better, right? So, yeah, indeed, that's a very powerful way to explain this in a simple way. And we talk about challenges and opportunities. So, what are the biggest challenges you faced as a researcher in this field, and how have you overcome them? Actually, you already talked a little bit about that, but is there anything else you want to add it?
No, I think the biggest challenge for me was the transition, as I mentioned, and learning new stuff, learning and trying to imagine what it really is, what everything means in a quantum system. Because honestly, you can memorize all you want,
Right.
all the rules, all the definitions, but that really is not a great help to you in the long run, especially if you want to dive so deep into the concept that you are using it, or you want to manipulate it or add something to it. So I think for me, that was one of the biggest challenges, and I had to break everything into very small parts. I watched a lot of tutorials, I read a lot of books. I had to train myself, because I'm really not great at memorizing. So I had to teach myself how to memorize, because, well, there are stuff that we need to memorize, but as mathematicians, we just work and keep practicing. And it's like the equations and the formulas they're part of you. It's like part of it's like driving. So you know how to drive. So you keep doing it. So you don't really think about memorizing anything, so to speak. But when it comes to physical concepts, I think there's more memorizing involved. So yeah, I had to use different techniques, flashcards and stuff like that to optimize my learning experience. But,
nice. Yeah, I really believe that. I've been discussing this with everyone quite, that mathematics is the most difficult subject, I believe, and field, really. Because in other fields, you usually have, like, do something in the lab and everything.
You can see it.
But in mathematics, you really just read numbers and you should understand that relationship, right? And so
it's funny you're saying that, but there's this famous quote from one human, and it says that you just get used to doing math.
Right.
It's not that it doesn't get easy. You just get used to it. It's like, okay, this is my motto for life now. You just have to get used to it, used to the pain. But no, I'm just joking about that part. But yeah, it's for sure a lot of practices, and it's a different process of learning for sure compared to many other sciences.
Right. Sure. No, of course. Yeah. Thank you. So let's talk about like you as a woman. Okay, as a woman in quantum computing, have you faced a unique challenge and experience, and how do you think we can actually encourage more diversity in this field?
Well, I agree that this field is very male-dominated, and I was always used to go into a classroom and I'd be the only woman, or at least there's another one. That's the maximum. And it's still the same, even though I transitioned to quantum computing. But if I've never faced any challenges, because I think I was always lucky in that sense, because I feel like when you're working with brilliant mind, and also the world is going towards this direction that people are valuing diversity and inclusion more and more, and try to actually practice it. And I think, that's a really good direction that we're all going to. But I've never faced any particular gender-related challenges, but to have more women and see more women in STEM fields, basically, I think one important way is to show them or have workshops or try to advertise it somehow and show all these women, younger people, that it is possible and you actually can do it with a little bit of practice. And unfortunately, sometimes some people have like these mindsets that limit themselves.
Right.
But I think nowadays it's getting better every day. And I'm really happy about that as a woman in science. And I think the more you try, us women in science, try to advertise it, try to be out there, try to show ourselves in the public and see, okay, this is what we can do. And I think that can help.
Nice.
To some extent.
Definitely. And then we, of course, treat everyone as a human, right?
Exactly.
Regardless of their gender, right? And hopefully, as you said, like in Canada and at least in the environment that we are here, we don't see that really anyone think that way.
Mm-hmm.
That they think, okay, if they are a man or woman or any other way that they actually identify themselves. So, yeah, that's great.
Yeah.
So let's move on to the impacts and the future of quantum computing. And my question is, what do you think will be the most significant impact of quantum computing in the next 10 to 20 years?
I think quantum computing is going to affect everything. It's going to affect the way most system works. And there is like a big hype about the quantum computers themselves, but that's only one basically result of quantum computing. Well, there's going to be big effects on material science, medicine, crypto, chemistry. And I think there's going to be big difference in all those areas.
Nice. Yeah, of course. Yeah, that's definitely, I agree with that. And what industry? You talked about some of those industries, but I'm thinking like in our province in Saskatchewan that we're living, right?
Mm-hmm.
So agriculture is one of the biggest area, and the economy of this province actually relies on that.
Mm-hmm. So
how can quantum computers help in, for example, in the field like agriculture and farming?
Well, personally, I have never worked on any projects like that, but I know for a fact that there are many optimization problems in agriculture. For example, I know a friend of mine was working on quinoa seed separation process for his project. And I know that can be modeled as an optimization problem, for example. And these optimization problems can actually be worked with or basically operated on quantum structures or quantum computers or softwares, you can also say. Like what they do at the D-Wave company. They are, or one qubit, they work on lots of optimization projects.
Right.
That's their main, and it's across industries, not just for agriculture, it's just for many different ones.
Right. So one of the challenges that we have for example, in the city that we see usually is about weather forecasting, right? So it happens a lot that you see, for example, look at the weather app on your phone, and you see that the chance of raining or snow going to be 100%, but you don't see the snow or rain, and tomorrow is like 20%, but it's actually a lot of rain that you see, right?
Yes. Yeah.
So probably if we can actually use the help of and power of quantum computers for weather forecasting, that would be one impact, right, in this field, right? And that definitely will be helpful. So farmers also know when to protect their crop, when they should harvest it, etc. Right?
For sure, they can have a better, a more detailed description or a better anticipation of what it's going to be. And it's not just for the limited to these areas, also for bigger issues such as climate change.
Right.
It can be applied, and I think so. That's
Yeah,
one of the
that's
important
indeed.
applications.
Yeah, actually, one of the big, like you see in summers, usually lots of fire in the forest, right?
Yeah.
So that makes a lot of people to leave their house, and actually they lose their property, they lose their and the livestock, right? So that's actually lots of challenges out there. So hopefully we can harvest that power and solve these big problems there. Yeah, thank you. So let's talk a little bit about the fun side and human side. If you could solve one big problem using quantum computing, what that would be? Let's say you just have one option.
Just one option. I think that would be something towards saving the environment and climate change or energy conservation in some way. That is also possible through material science.
Of course.
So I think, that's what I would do.
Right.
Something for the planet.
Yeah, that's very inspiring. Of course, that's a good one. Yeah, yeah. And let's say outside of your work, I know that including those hard times that you might have, what type of hobbies do you do to make yourself calm, and also beyond that, academia?
Yeah, well, I'm a musician, and I've always been working in different fields of music, and I remember back in my bachelor, there was this point that I wanted to switch to music. I didn't ended up doing it, but it was a very big dilemma for me. But I decided to take this path, math, and but always stick to my music career as well. So I've learned different instruments. I've worked with different choirs, singing groups, and so I've always kept busy with music. And other than that, philosophy. I love reading philosophical books and psychology.
Nice.
And yeah.
Nice. And actually, just to tell the audience that you had the channel, I believe, in Spotify, right?
Yes. Yeah. I've.
So usually you put the recording and publish it there. Right?
Yeah, I do write music from time to time. I've never earned any money through my music career, but it's just something that I really love to do, and I write music and I compose. And I published my first album in 2 summers ago.
Right. Nice.
Yeah.
That's great.
Yeah.
So that's actually a good message, because you mean it is possible to be a scientist, but at the same time do other hobbies as well, and even professionally, like you follow music, right?
Mm-hmm.
So,
I think it's very essential to do that, because it's good for your brain. Even if you have hobbies that are different than what you're doing, it's a good reset for your brain.
Right.
So you give yourself the time and chance to have the fun and also keep your creative part alive, which you also can use in your scientific and fields. And I don't see it as wasting time, for sure, even if you have to spend a little bit more time than you want to, because the effects are greater than you might even guess. So yeah, I'm grateful for keeping that in my life.
Right. No, indeed. Yeah, that's great. And we talked about what it really is exciting about this field, but is there how do you see yourself in 10 to 20 years?
Okay, this is one of those questions that can change from year to year. But I for sure see myself as someone who try to, even if not successful, try to find new ways to make our lives better. help the environment, help the climate change, and to have an impact on crucial facts in life, such as that. I think that's where I see myself. And also another thing that I really would love to do, I always have loved to simplify things as much as I can when I'm teaching or a course in math. And you always get that, I hate math, no. But I always want to show people it's not as bad as you think. You just have to look at it differently. And I always want to be someone who shows others the real picture of math and quantum physics and any research in this field. So in hope to encourage them to take this path as well.
Nice. Yeah, indeed, that's very inspiring. Thank you. Yeah, so let's have a break and then we'll be back with the second part and we'll talk more about the technical side of quantum computing. Yeah, thank you.
Yeah, sure.
Okay, welcome back to the second part of this interview. In the first part, we talked with Mandana about the quantum computing more from the personal perspective. So just to know more about our audience and what she's doing and talking about more the academic perspective, but now we move on to the technical side. And let's start with what is actually quantum computing?
I think quantum computing can be defined as a sort of computing that is based on quantum mechanical principles. For instance, in classical computation, we have bits that are either zeros or ones. And but in quantum computing, you're dealing with qubits, which are also known as the quantum bits. And the main difference is that the quantum bits can be, it shouldn't necessarily just be 0 or 1 like the classical ones. It can be in a superposition, is the terminology that we use, of both of these states. And superposition, like I explained earlier, that you're just pressing a few notes of a musical instrument and have the harmonies, like having all the quantum states at the same time, but there are different proportions of each one of them. And yeah, there are some characteristics of these kind of principles. Basically, one of them is the superposition, one is the entanglement.
Right.
And these are the important parts. Yeah.
So we know that in a classical computer, we usually work with, as you said, about 0 and 1, right? Mm-hmm. So those are just, you can say, transistors, or you can say the set of the light that you turn them on and off, and based on that, you do some computation. How do you how can you do this in a quantum computer? Like, if you can think about it as like the transistor that we do in a classical computer, how we can do it in a quantum computer? In terms of the fact that in quantum computers we're working with like light, with photon, for example, or electron, right? Mm-hmm. So can you?
So, to my knowledge, what you can. So, are you meaning that how we can see this duality of the
right? Let's actually
like,
bring it to this point. You talked before about Schrödinger, right?
Mm-hmm.
He had that experiment, not experiment actually, but that explanation how about that cat that was trapped. Mm-hmm. Can you like discuss it like from that perspective?
Yeah, well, according to that famous experiment, if you want to know what it means to not know what's happening in a system unless you measure it or unless you observe it, that's basically the main principle. And in the Schrödinger's cat experiment, you consider a box and you have no way to see what's inside, and there is a cat in there. And if the box is closed and you have no way of seeing, you don't know if the cat is dead or alive. And that's basically that duality when you say, okay, it can be either dead or alive at the same time. So that's where the magic comes from. That's where you can say, okay, this is what it means to be in a superposition of both the states until you open the box, disturb the system, and you observe the cat and say, okay, the cat is in the being alive state, basically. So that's what it means, basically,
Right.
like a experiment.
So here it means like if we have this qubits, right? So we don't know if it's gonna be 0 or 1 unless we measure it, right? And then we realize that it's gonna collapse either to one of these two states, right?
Right.
Okay. So of course. The superpower of quantum computers, right? We talk about, for example, superposition. We talk about entanglement usually and interference. Can you explain like how this makes it different and more powerful? Like I just referring to some diagrams and some numbers from IBM. So comparing a qubit and how we can do it with the classical computer, how many bits you need with the classical computer. So with 2 qubits, it's equal to 512 bits in the classical bits that you can represent that entangled state.
Mm-hmm.
And if you increase it to 100 qubits, it means that you need more than all the atoms in the Earth to actually represent that entangled state. And if you go a little bit further to 180 qubits, that's going to be more than all the atoms in the entire universe. So it means that in a classical computer, it's very hard to represent that entangled situation, right? So can you elaborate in total, like where that power comes from?
Yeah, well, like you mentioned, it's coming from the main characteristics of quantum systems, which is superposition and entanglement. And superposition we went over it a few times. So that enables being the system being in multiple states at the same time.
Right.
That speeds things up. Because in a classical computer, you either can have a 0 or a 1. So
Right.
you have a fixed array of, I don't know, if you're dealing with 100 bits, you have a fixed array. But if you're dealing with a quantum computation, you can have different states at the same time. So that exponentially speeds things up. And that's where the speed comes from. And the entanglement, it's another magical properties of quantum system, and it means doesn't matter how far 2 particles are from one another, but if they are entangled, the state of one can affect the state of the other. So for example, if I'm on Earth, and I'm entangled with another being in somewhere across the galaxy, and then my state, the change in my state will affect that, basically the other state as well. And that's also was very mind-blowing, and one of the very basically interesting
Right.
characteristic of the quantum system that also,
Right.
yeah.
And it kind of like sparked a lot of conversation around scientists back in the 20s, right? So specifically, we're talking about the conversation around Einstein and Bohr, and Schrodinger as well, right? About this spooky action that Einstein was referring,
yes.
right?
Yeah.
So kind of like very interesting how this discussion already been. I mean, the first time that people start to talk about quantum computers probably has already been around the century, like 100 years. But yeah, and here we are. People finally see that a lot of this property actually, they can apply it in their real life, right? So
For sure.
yeah. So which aspects of the or which sort of problem we talked about some of them? Can we get a little bit deeper into other type of problems too? For example, let's say what D-Wave is doing, right? In terms of optimization or in terms of logistics. That I mean, like the routing the packages or sending the packages through different ways, right? Through different paths. That's again type of optimization problem. Or in chemistry, we know that if you want to simulate like the water molecule, that becomes a very hard problem for our classical computer. But with a quantum computer, that's actually a very easy problem because we are directly working with the atoms itself.
Yes, exactly.
So can you explain in any other application like that you've been observing or you've been reading about, like how they can solve this problem and what type of problem they can actually solve?
So I think I can mention the application in material sciences, which is something that I've been focusing on lately. It's the how finding new structures, new quantum structures. Again, the same quantum structures that follow the rules of quantum world, following the quantum fundamentals, basically. So these new materials can be used in so many different ways. They can be used for superconductors. They can be used in computer circuits. They can be used for batteries with a longer lifetime. So depending on which area of work those materials are being used for, then these new structures, these new one can also call them metamaterials as well, which is a huge field for itself, that these structures follow very specific behavior, and that is very rare in quantum world because everything is very chaotic to some extent. So those specific structures can be used in these materials, and it's a breakthrough.
Right.
Yeah, and I think that's one of the greatest actually applications. Yeah.
Right. So I know some of this like airplane designers and manufacturer. So they test their airplane for the wind tunnels, for example. So they understand the aerodynamics of the airplanes and how they can better design their airplanes to have less friction or have a higher speed and better aerodynamics. So it applies literally in everything, right? Specifically, you mentioned more about manufacturing and material science, and indeed that's a huge advantage,
Yeah,
right?
for sure.
Right. So here I just, we said like quantum computers being on the, like there's been lots of discussion for decades around this, but it was actually in 1994 with Shor's algorithm that people saw the first application of a quantum computer in solving real problems, and that was factoring prime numbers. Because in the public cryptography, we know that if we multiply two prime numbers, then factoring that number is a challenging problem. And sometimes, then that's what makes actually the security in our internet. So breaking that, factoring that large number with a classical computer gonna takes us billions of years. And actually that's quite an, not impossible, but infeasible problem. But we know that after Shor actually had this algorithm out there, we realized that we can break this algorithm even within minutes. So that's why all this discussion around this came to play, that we have to move to quantum safe cryptography and make things secure, right?
Yes.
And beside this also Grover was another one in 1996 that they explained that we can optimize the search through unsorted databases.
Yeah.
And that's another impact, of course, in lots of problems that we have normally, right?
Yes, for sure. Yeah, one of the greatest applications is on crypto, as I mentioned.
Right.
Yeah, for sure. Making these algorithms like there is actually this main field of algorithm developer, which scientists are daily working on making these algorithms better and better, that are the backbone of these quantum computers, and that can be used for, they introduced so many different packages for programming that you can use, like companies like Xanadu. I know they're actively developing their algorithms, which is very important, actually.
Right. Now, because we also had a question around the application security in comments on LinkedIn page, and I want to just elaborate a little bit on that because I'm working with quantum security and quantum cryptography. So the goal is that if you're using public cryptography, they can be broken in the future. So that's now we should move on to what NIST recommended. They already have introduced some cipher sets that we should start to utilize them in our industry actually today, because we have the concept of data harvesting, which means that you can store the data today, and whenever you have a powerful quantum computer, you can try to return it to the plain text and convert it to the plain text. So this makes it very important concept because we have lots of security right around that is about our conversation, is about our healthcare data, is about our personal information, or like our emails, date of birth, SIN number, and etc. So I hope that companies actually start as soon as possible and do this to make sure that we are secure against like the power that comes to the play. So let's, before moving on, I just want to wrap the session with some quotes from some brilliant scientists in this field. Starting from Richard Feynman, that is someone that you're inspired by. So Richard Feynman says, nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look easy. So I guess like as a human, like we are curious about solving whatever that looks very hard, right?
Yeah. Well, it for sure this code shows his resilience in facing so many different hard problems.
Right.
And what I love most about him is how he always tried to simplify things and make them accessible to a more general audience or more people, more scientists. With the diagrams when he created, and that those diagrams kind of wrap up every sort of interactions one can come across. And it's funny, I was watching one of his interviews, he was also saying that I'm just an ordinary person. He won a couple of Nobel Prizes, and he's just like, I'm just an ordinary person who is resilient enough, who's stubborn in making way and practice and hard work. So yeah, that's why I really endorse him.
Right. And actually he has a lot of, you see lots of tutorials of him. It's still available online that he's talking about the physics and quantum mechanics, right?
Yes,
So it's actually very inspiring. Many decades ago, and still you find it very, very powerful. And I mean, you barely can find someone that can bring it and explain it in such a way, right?
Yes, so, of course,
Right. So there are a couple of other quotes that I want to quickly review. One of them is David Deutsch, that says, quantum computation is a distinctly new way of harnessing nature. It will be the first technology that allows useful tasks to be performed in a collaboration between parallel universes. You want to elaborate anything on that?
I'm really not an expert in that field, but I do find it very interesting that as I called all these features of quantum systems magical, for sure, most of the things that are not very well known to us and we don't believe them, or because we haven't seen them simply. So many of these things can be justified by all these new rules that can be applied to so many different things, to everything. And I don't know much about parallel universes, to be honest, that I can broadcast, but I know that there are ways that physicists can talk about that, and that also has something with the wormholes and the black holes and the where you can be around the event horizon. I do just some fun light reading sometimes.
Right.
Yes. It's all very...
So the thing is that you see, I've been following Michio Kaku, that actually is one of the most active scientists in this field today, especially because he worked in the string theory and also had a lot of these interviews and seminars and conferences talking about quantum computers. So he always say, if we want to solve the nature problem, we have to use nature way. Nature doesn't understand 0 and 1. Nature understands atoms, right? So we have to better to do it the way that nature solved those problems, including from photosynthesis to any other problems that we really have in nature. So that's actually very
That's
inspiring.
very interesting and inspiring, yeah.
Yeah, indeed. Yeah, sure. So, there are lots of other codes, but I don't want to go through all of them. But just want to ask you, is there any resource that you suggest people, especially for those who are not expert in this field, or maybe they don't know anything about quantum computers, that they just heard about these terms, where they should start, in your opinion?
Well, there are millions and millions of videos out there, right? To teach you what it means and what the whole things are about, what are the concepts and everything. But if you're a reader, you can also go over some classical textbooks for physics if you want to dive deeper. There are also some books that have a they're for a general audience. So those books can be very helpful. Videos, that at least that's how I learn things. I took courses. There are so many online courses. If you love programming or you love software development, like you want to know more about those, again, big companies like Xanadu, like D-Wave, they do have this public resources for everyone. And I have to say I've learned a lot about those. IBM has so many online courses, and everything is free for you to just go and read. And IBM, I just remember that for they have this platform, they have videos, they have notes, they have practice questions. Right. You can access their online platform to actually code, which is called Qiskit. Right. So you can use that one to practice if you are into that. But yeah, there are so many different areas in quantum, and depending on what you like to do, there are different resources. Of course. Yeah.
So that's good that you mentioned about especially IBM here, because you can just visit their website and they have this Qiskit that you can run it on Jupyter. And you can actually not just simulation, you can run real quantum computers with more than 100 qubits. Like one of them is 127 qubits that you can run actually today. Mm-hmm. And every month they give you some free window that you can run it and test it. Like how can you solve this problem? So those are great opportunities. And in terms of let's say, in industry, like you see, today there is a lot of conversation around AI. So lots of investment in this field, and of course that's reasonable because we see the impact right away, and people know that they're gonna find their paying customer out there. But how can we encourage the industry? Actually, do you think that so they see that in the very close future, they don't have to wait for 50 years. In a very close future, they can see that return on investment. Like you see back in 1960s and 70s that IBM was one of the pioneers in the field of classical computers. Mm-hmm. A lot of people didn't know how would be the future. So they didn't know that it's going to change our life. But actually they did. And now we cannot live without computers. So do you think in the future it will be like that? Let's say maybe in a decade or less than a decade, even more. But eventually, do you think it will be like that? That we do lots of our tasks with quantum computers?
Well, I believe everything is possible for sure. And we've came so far from the start, if you consider the starting point of quantum computation. We came so far, and we actually are starting to see applications. We can actually see how they change. And, well, if they're applied to materials, for instance, you can use the materials in X-rays, in photonics, and even in circuits to make them better. So I think, yes, yeah, I think there's a high chance of the whole quantum computation revolutionizing everything. And there's a big hype around it these days, and as you mentioned, it is the year of quantum computation.
Right.
So I think many scientists, many people believe in that. So
right.
I think
so
yeah.
I put it this way, like you see, there's been a question that, am I gonna see like a quantum computer on my disk in the future, or is not gonna be the case? I'm just remotely connecting to a quantum computer and just run my task for what that quantum computer is more suitable for, right? And do you have any comment around that?
Well, to have the quantum computer on your desk, I don't think that will happen in near future, at least.
Right.
For sure, giving enough time, every science can lead to many progresses,
right.
of course. But I think the main takeout of quantum computation is that we need to use it in the way that we just started, and this is good enough, because having the quantum computer on your desk, well, if you can operate it remotely and it's working and it's faster for the purposes that you want, so that is good enough. And it is gonna get better. The bigger companies, they're applying more and more qubits. They're trying to expand their computers, but we also have to note that there are many limitations to quantum computers. They're very sensitive. It's very hard. The bigger they get, the harder it gets to keep the coherence between the system, avoiding noise. So there are many limitations, and the temperature also is another problem. And I personally don't see that as a big problem. I mean, if you can make your way without having the computer on your desk, just keep doing what you can at the moment till, well, we get to that part. Because if you're using that to get better materials for the computers, well, eventually we're moving towards that direction. Right. So I think it's best to focus on these fields that you're doing at the moment.
Right. So you see, the first classical computer that we had, they were the size of a room, right?
Exactly.
You see that a large room with just piece of a computer, because we couldn't make it as small until we could have the transistor that we could make it smaller and smaller, and now we have a computer that you can have it on your wristband, right? So I think eventually we'll go through towards that way. I mean, not that we need to have that with us all the time, but it's still for the problems that our classical computer can solve.
Yes. Yeah.
Right?
Yeah, absolutely.
Yeah, sure. Thank you very much, Mandana, for being with us today.
Yeah, of course.
So this was
Pleasure.
a very pleasure to have you here. We learned a lot, and I hope that the audience enjoyed this program too. So if you have any more question about this interview and you want to ask Mandana more question, I'll post some any other methods, communication way that you can actually connect with her. Either you want to also enter for your graduate study to this field, or any other question that you might have. Yeah, and that's all for our first episode. Thank you very much for watching us today.
Thanks for
having me. Thank you.